fifth algebra, differential equations, and sociology 101. And then I'm going to take a blow-off volleyball one credit class because all my teammates wanted to do it.
I need to talk with Jensen about possibly going into optics, but
Which car?
figuring out how it'll fit.
Yeah.
I kind of have to do differential and quantum.
Yeah, that's a lot. Hopefully we can offer that class again one day.
Hopefully this next year we'll get a bunch of new physics freshman students.
A new what?
A bunch of new physics engineering students.
There should be plenty, actually.
And that's just us. Us and Jackie and probably like two more.
I thought Jackie was engineer.
Who's engineering and physics?
She can't. She can be one or the other.
I think she's like a
I think
That's
she-
Oh, she's one of the last ones. But she's the only that got into applied physics. Oh, she's in the limbo. The applied physics major only lasted like a 1 year. It was only on the books for 1 year. So we thought we didn't have. No, so it will be Jackie and Scott are the only two applied physics majors. So we have a bunch of classes that we need to open just for them.
She was talking about her schedule. She's just like struggling to figure out what to like take because what you're saying, you gotta open some classes for them.
Yeah. Okay. So we finally are gonna start with the second half of the class. It took us a while to get here, and we're gonna be talking about magnetostatics. Okay, so basically we're gonna start talking about magnetic fields. We're gonna start talking about how the magnetic fields are created. How can we calculate magnetic fields and different configurations? And we're gonna find some equations that are kind of similar to the electrostatics equation that we have seen. So there's an equivalent of Coulomb's law, there's an equivalent of Gauss' law. So there's something like that that we're gonna be talking about. So even though we get to magnetostatics quite late in the semester, I think we should be able to move relatively easy. It is hard, like all these semesters been hard. It's just a bunch of vectors, algebra, calculus, weird integrals that just appear, and we just need to solve it. Okay. So I'm guessing you guys saw a little bit of magnetism in 122, something like that. You could solve Lorentz force.
4 years ago.
Lorentz force rings a bell.
E cross L or something like that.
E cross L, something like that, yeah. Okay, so one of the things that we know is that if we have a wire and through that wire we have a current, then that current is going to create a magnetic field. Okay, and what we need to find out is, given a point P, what will be the magnetic field at point P created by the current I. Okay, this is similar than the Coulomb's problem. So we have a charge and we want to find out what is the electric field created by that charge at a point P. So it's something similar like that. So one of the big differences is that, remember, the current is charge that is moving, so we need to have moving charge to create that magnetic field. Now, depending on the book that you read, and if you see videos about that, they talk about magnetic fields and stuff like that, there are two main variables that we're going to be working, H and B. Okay, H is the magnetic field. And it's usually measured in amperes per meter. And it's kind of the equivalent of what we talk about when we talk about the electric field. Okay. B is what we call the magnetic field density. And is measured in Teslas. And it's very similar to our electric displacement. Remember, the electric displacement, another name for electric displacements is the electric field density. So, but they are very similar, they're kind of equivalent. Okay, remember that when we're talking about the electric displacement, the way we can calculate it is the electric field times E naught times the polarization of a material. So when we have an electric field inside a material, we're going to have a polarization field, and that field is going to increase the electric field that we have in free space. So there's combination of those two create electric displacement. In free space, the polarization is going to be 0, and then the electric displacement is just going to be epsilon naught times electric field. Okay. With the magnetic field density, we're going to have something similar. The magnetic field density, B, is going to be equals to mu naught, that is a new variable that we'll talk about in a minute. And then we're going to have the magnetic field plus the magnetization field. But we're going to talk about that later. Okay, so it is very similar to the idea of the polarization. So when you have a magnetic field inside of a material, if the material has some magnetic properties, it's going to create an additional magnetic field, and that's going to be added to the magnetic field in free space. So in free space, in the absence of that material, this M vector is going to be 0, and the magnetic field density B is just going to be equals to mu naught times H. Okay, mu naught is the permeability of a material. Okay, the value of this thing is going to be 4 pi times 10 to the minus 7 Tesla meter per ampere, which is a weird unit. Okay, so where is the confusion? Sometimes, and it's very common when you see it, that people talk about B and H like it were the same thing. They talk about like, this is the magnetic field B, this is the magnetic field H, and technically they are not. They are small difference when you talk about this, especially when you're talking about in materials. But when people solve problems in free space, they treat them like they were exactly the same thing, and that's not necessarily true. So I'm gonna try to be careful, make sure to make the distinction, and just let's keep track that there's one thing that's called the magnetic field density, measured in Teslas, and then another thing, there's the magnetic field that's gonna be measured in amperes per meter. Okay. Okay, so we have this current going through the wire. We want to calculate the magnetic field, and the equation that we can use to calculate the magnetic field is what is called the Biot-Savart law.
I remember that.
Yep. So I wonder how much you guys saw on that class.
I remember seeing that equation. I don't remember if we actually ended up using it. I think it might have been something that like we did at the end of class, like the end of that term, just kind of like not on the exam. But
Yeah.
This is something.
Yeah, this is stuff I haven't seen in years, so.
And the equation to calculate the Biot-Savart is going to be I over 4 pi times L cross R over R squared. And I'm going to explain a little bit what does that mean. Okay, so I have my wire, and my wire is going to have a different shape, and I want to calculate the the magnetic field at point P. So what I'm going to do, and I know that I'm going to have a current going through this wire. So what I do is that I'm going to take a little piece of this wire, a DL, and I'm going to look at my current there at that point, and then the distance from that point from that differential L to my point P, that's going to be R. So the idea is that I can treat these differential segments of the wire like if they were point currents, like little tiny ones. And then what I need to do to calculate the magnetic field is just add the contributions of all of them. So I can rewrite this expression of my magnetic field as a differential DH. It's going to be the current 4 pi dl cross r over r hat. Okay. Sometimes you will see it that instead of working with H, we can also work with B. So we can say that dV, the magnetic field density, that's going to be mu naught I over 4 pi dl cross r hat over r squared. Okay. So the Biot-Savart law is very similar or equivalent to Coulomb's law. Okay, it helps us find magnetic fields with any arbitrary configuration of currents. So it doesn't matter where the current goes or what will be the path, as long as we can find a function to integrate, as long as we can find an expression for DL, we can find the point everywhere. But the integrations can be very nasty. It can be very long and not so easy. eventually what we're going to be talking about is the same way that we found Gauss law, that Gauss law helped us to find solutions for problems with high symmetry. We can use an equivalent of Gauss law, but for magnetic fields, which is called Ampere's law. Okay, so we're going to see that hopefully at the end of the class or Friday. So we're going to do a couple of problems using Biot-Savart law. We're going to do the classic problems. There is the infinite wire, a non-infinite wire, and then I'm going to do a loop. And those are the classic problems. And I'm going to try to do it in different ways so you can see different techniques to try to solve it. Okay? Nika, don't fall asleep. Okay, so I'm going to assume an infinite wire along the y direction. And I'm going to have here a point P along the x-axis. And I'm going to say that this point P is at a distance a from my wire. Okay, I'm going to say that the current goes in this direction. But I want to know what is the magnetic field at point P. Okay, one of the things that we can do working with these kind of problems, even before we start doing any calculations, is to use the right-hand rule. You guys remember that?
Oh, yeah.
So you have your thumb pointing in the direction of the current, and then whatever your fingers cross, or whatever your fingers curve, that would be the direction of the magnetic field. So in this case, at point P, the magnetic field will go into the paper. So the magnetic field will go something like this. Notice that in the opposite side of the wire, the magnetic field will come out. So on this side, it will be coming into the paper. Here, it will come out. Okay, we should be able to get that direction from the equation. So we will, but this will help us kind of like figure out the right direction. Okay, so I'm gonna come up with a differential DL, and I'm gonna say my DL is gonna be somewhere around here, and the vector R is gonna be this guy over here. Okay, and I'm gonna find my expression for the electric field, and I'm gonna have that DH is gonna be the current 4 pi dl cross r hat over r square. Okay, in this case, I'm assuming that the current is constant, but I can have the current to be variable, so that can always make the problems a little bit more complicated. To calculate the total magnetic field, I'm going to integrate on both sides. So the magnetic field will be the integral from the length of the wire, which in this case will be minus infinity to infinity, of I over 4 pi dl cross r hat r square. Obviously, these first terms are constants. And I have that little mess. Okay, so what can I do from here? Well, one of the things that I'm gonna rewrite dl. So dl, this differential gonna be, I can express this as a differential dy in the y hat direction. And r squared, this distance, I can say, well, this thing is going to be a squared plus y squared. Okay. Another thing that I can do is, okay, I know that dl cross r hat, that's going to be the same as dl, well, the magnitude of dl times the magnitude of r hat, then sine of theta. And sine of theta, well, if my theta would be this guy over here, and sine of theta will be a over, no, yes, a over r. Yeah. So I can combine all these things, and I'm gonna find an expression for the magnetic field. That's gonna be the current over 4 pi. Then I'm gonna have the integral from minus infinity to infinity. dl cross r, I know that that's gonna be the same as dy sine of theta. So there's gonna be dya over r cubed. And this will be do. I know we have been doing this like for 7 weeks now, but do you want me to do a bigger handwriting? Or is this okay?
That's good.
Okay. Okay, the A is a constant, so I can simplify this a little bit. And this will be IA 4 pi integral minus infinity to infinity of dy a squared plus y squared, 3/2.
Oh, no.
Oh yeah.
Oh. Oh.
We did this some time ago. I don't know if you guys remember.
Yes.
Sadly, I do. I don't know.
Do you want to try to solve this on your own?
So, let me flip back to early. Yep, there it is. Hi, E is equal to 2L over L squared plus C squared square root.
So I'm gonna say, so I'm gonna go from this triangle that I have over here. This is Y, this is A, this is R. Okay, and I'm gonna have a variable here. I'm gonna call phi. That's gonna be the angle they're gonna be using. So based on this angle, tangent of phi will be Y over A. Yeah, so I'm gonna say that Y is A tangent of phi. So I'm gonna do a small change of variables. And if that's the case, then dy will be A secant square of phi d phi. You got phi or phi?
I said 5, but I think that's wrong.
Phi.
I don't know. I said in Spanish because I don't know how to say it in English. So
Phi.
phi?
That's how I say it as well.
Okay.
Phi.
I don't hear everyone else say it.
Most people say phi. But that's just it.
But it's the same with pi. Everybody say pi when it's supposed to be p.
Actually, I'm not too worried about it, but
It's just like I know like I'm Greek, so if I say
You come.
letters, I'm just like, the worst one is in biology when you say chai. I'm just like, oh.
Okay.
Chai.
So phi, we're gonna call it phi. Okay. So I have this, and then I can rewrite this guy over here. A squared plus y squared to the 3/2. That's gonna be the same as a squared plus a squared or a squared tangent square of theta to the 3/2. And this will be a squared 1 plus tangent square of theta,
Is it theta now?
phi, sorry.
I wrote a squared plus a squared. And I thought it was like the tangent I was writing for a second. Like, wait. No, it's just half squared.
And 1 plus tangent square of phi, that's secant square of phi. Okay, so H, so the magnetic field will be A 4 pi. The integral, I'll figure out the limits of integration now in a minute. So dy will be A secant square phi d phi, and then we'll have a square secant square of phi to the 3/2. Now, if I'm using phi and I'm integrating and making my y completely infinite, then phi will be pi over 2, and then on the negative will be negative pi over 2. So my limits of integration will be minus pi over 2 over pi over 2. Okay, actually this simplified pretty nice. It will be 1 over a over 4 pi integral pi over 2 a secant square phi d phi, and here we'll have a cube secant cube of phi. And this will be 1a 4 pi a square, or this is cube, secant of phi d phi. Okay, one of these a's are going to cancel with this one, and then I'm going to end up with I over 4 pi A, the integral of d and d phi over second phi. And this one is cosine, right? And that's nice. Mm-hmm. And that would be 2. Okay, and we say that that was going to be in the C direction. Negative C. Okay. Good. Okay. The second problem that is also very similar is calculating the magnetic field of a non-infinite wire. Okay, so I'm gonna just set it up in a different arrangement. So I'm gonna have a wire like this, and I want to find point P. And I'm gonna assume that that point P is not even center on the wire. Okay, so I'm gonna have an angle theta1 over here, and I'm gonna have an angle theta2, and that's gonna set up the limits. Okay, so again, I'm gonna start with my differential. I'm gonna have just small little pieces, and this is gonna be I over 4 pi times dl cross r hat over r square. I'm gonna say I'm gonna say that the distance between the wire and P, that's gonna be a distance A, and this is gonna be along the x-axis. So notice that in this case, if the current is flowing in this direction, in the positive x direction, then the magnetic field is going to be coming out of the blackboard. It's coming out of the paper. Okay, so we're going to have magnetic field kind of like that. Okay. You're going to try it? Okay.
I mean, you can Try.
So the integral, again, we're gonna have an integral of I over 4 pi dl cross r hat over r squared. Okay, dl, same as before, is gonna be dx, dx in the x hat direction. And r will be a squared plus x squared square root of that. And dl cross r hat, that's going to be magnitude of dl cross the magnitude of r hat sine of phi. And now I'm going to go phi this guy over here. Okay, notice that sine of phi is going to be the same as cosine of theta, just because there are complementary angles. And this cosine of theta, that will be x over r. No, a over r. Okay, so again, I can have my magnetic field. I choose magnetic field, that will be the current times 4 pi. And then I'm gonna try to express everything in terms of theta. So I'm gonna have, my limits of integration will be theta 1 to theta 2. And I'm gonna have dl cosine of theta over r squared. Okay, so we have this equation. It's very similar to the one that we had before. So what we did before is we want to express everything in terms of x, and then once we have that x, we do the integration. So I'm going to try to do the same thing, but now what I'm going to try to do is to express everything in terms of theta, just because I want those limits of integration. Okay, so I know that cosine of theta is going to be a over r. So from here, I can say that r will be a secant of theta. Okay, I can also say that tangent of theta, that's going to be x over a. So x will be a tangent of theta, and dx will be a secant square of theta, d theta. Gonna do this 4 pi. And here I would have, where did I put it? Dx x hat cosine of theta over r squared over square. I think I have it. Okay, so now I'm gonna substitute this expression that depend only on theta. So I'm gonna have a square secant square of theta times a square times a secant square of theta cosine of theta d theta. Yeah. So this a is going to cancel with this secant square is going to cancel with this, and then we're going to end up with I 4 pi a integrals minus theta 1 over theta 2 cosine of theta d theta. So this will be a over 4 pi a sine of theta 2 minus sine of theta 1. Okay.
And if we knew those angles, then we'd be able to plug those in.
Yeah.
A little more reduced.
Yeah, if you have the dimensions and you know the distance A, then you can calculate these angles, and then you can find that magnetic field. And the same thing, if you assume that you have an infinite wire, then you can substitute here pi over 2 both sides, and then you end up with the same equation that we had before. The advantage is that this one is a little more general, and basically you are not assuming that you're going to be center on the wire. Okay. Make sense? I know.
I'm having fun.
You're having fun.
Not being sleep deprived, it's gonna be great in 2 weeks.
Why?
Footballs, we have like a week and a half left.
Oh, so you will be done with football?
Yeah, and that means I can actually get sleep. 6:30 meetings are fun.
You guys do any sports in the fall, in the winter?
I mean, we do like lifting, but nothing serious.
Okay.
We have daylight savings in the week too.
What you guys
It's
done
after our game, though, our last game, thankfully.
this week? Next week?
It's next Sunday, it's daylight savings.
Oh.
Yeah.
Does that mean we get an extra?
So we're gonna be living,
No.
so it's gonna be darker sooner?
Get one less?
One less?
Cause, oh no, we did get one more. All that.
Yeah,
Yeah,
that's what I need.
because we're getting off of daylight savings. Because who needs longer, or, yeah. Yeah, bright and early in the morning.
Yeah, 6 a.m. practices.
Okay.
I love it. I wish those practice exams are just meetings. Because extra practice, you're at least like up, you're like,
Yeah, so you can still do sleep.
parse the extra meetings. Then there's like this, I get up at 6:30, biology, physics, then political science, all
one after the other.
pretty much.
Oh, from political science, you must be like really awake.
Yeah.
For that one, after.
Oh, that's gotta be interesting.
Back to home too.
Okay, so we have a circular wire. It's gonna be doing a loop, and right now I'm assuming there's just a single loop. I'm not. You can imagine that there's a wire going here, the current's going counterclockwise, and then it's coming out from another wire. But those extra wires, we don't necessarily care much about it. I'm going to assume that the current is going to go this direction. Yeah, so.
That's coming out, right?
Well, it depends. You are in the top, looking at the current at the top, it's coming down. But if you're looking at the current here, it's going to go like this. If you look at the current on the bottom, it's going to come all the way. So the magnetic field actually is going to have a weird shape. Well, a weird direction. So this is going to be my vector R. And the magnetic field, it's going to be like something like this. Okay. And as we move across the loop, this magnetic field is also going to be moving. Okay. You can think that as we add all the contributions of dl, all the y components of the magnetic field are going to cancel, and then we only going to end up with the x component of the magnetic field. Okay, I'm going to say that this angle is theta. And if that angle is theta, this angle is also going to be theta. So here we have a triangle rectangle. One side we have the distance to point P, the other one we have the radius R, and then the distance to the point P, lowercase r. And I have this angle theta. Okay, so apply and bios of that. The H will be I over 4 pi dl cross r hat over r squared. Okay, I only need the x component of this vector. So that will be, the x component will be the same thing times cosine of theta. Okay, now this dl cross r hat. Well, r hat is pointing in this direction, and dl is going to be tangential to the loop. So this angle is always going to be 90 degrees, no matter where you are. So this dl cross r hat, this is only going to be dl. Okay, so I'm going to have this hat, it's going to be I over 4 pi dl r squared cosine of theta. Okay, so cosine of theta, if I'm using this arrangement, cosine of theta will be r, the radius, divided by the distance, lowercase r. The distance r, lowercase r, that will be a squared plus r squared, square of that. Okay, so I have a definition for theta, I have a definition for this guy, dl. So I have section of my wire, and this will be the L, right? So if I call this phi, then dl will be r times d phi. So it's just that section of my arc. Yeah. Okay, so now in 5 minutes I have to finish this. I'm gonna have the magnetic field in the x direction will be I over 4 pi, and then the integral of, I'm gonna have dl, this is gonna be r d phi times cosine of theta. That's gonna be r over r squared over r squared. So I'm gonna have a plus 3 halves okay. It looks like a nasty integral, but we are integrating with respect of d phi. A is a distance from the point, so that's a constant. R is going to be the radius of the loop, so that's another constant. So all this is just going to be a constant. So I'm going to have I over 4 pi r squared over a squared r squared 3 halves. And then the integral of d phi. D phi, remember, is helping me calculate the length of the loop. So this is just going to be from 0 to 2 pi. So that's just going to be 2 pi. So that would be I r squared 2 a squared plus r squared to the 3 halves. Okay, if a equals 0, so if I want to calculate the magnetic field at the center of that loop, then the magnetic field will be I over 2r. Yeah. Yeah, any questions? No? Okay. So we're gonna stop here.